Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello. So it's my pleasure to have Karl Friedrich Bolz here today from University of Düsseldorf in Germany. So he's been working on PyPy. So he's in fact one of the core or the core developer of the PyPy project nowadays.
No.
One of the core developers. Okay. So he will talk about the approach in PyPy and dynamic languages and tracing JITs. He's visiting us for 4 days, so if you want to talk with him later on, just tell me and we can schedule a meeting with him. Okay, please go ahead.
So thanks very much. Like I said, I've been working on PyPy for the last, I think it's pretty much 6 years now. And I learned a few things about implementing dynamic languages during that time. So for this talk, I tried to sort of summarize a bit what the specific problems of implementing dynamic languages are. And this is very much thinking in progress. So if you have any comments or questions, just feel free to interrupt me at any time. So the talk is about how to implement dynamic languages in a good way with a focus on complicated dynamic languages because most of the currently interesting ones are rather complex. Also in a context where you cannot just throw arbitrarily much money at the problem, like an academic project or an open source project or even a domain-specific language. I'm mostly going to focus on imperative object-oriented languages, and I'm not going to talk at all about multi-threading issues because it's just yet another large field. So the goals of such implementations are that you want to reconcile flexibility and maintainability of the implementation because languages quite often will evolve. You also want your implementation to be simple because your team is going to be small. And of course, you want performance. So the talk is going to be split into 3 parts. In the first part, I'm going to summarize and analyze the specific difficulties that you get if you have to implement a dynamic language. In the second part, I'm going to compare and contrast various approaches that people have been chosen to implement a dynamic language. And in the third part, I'm going to talk about the PyPy project that I'm involved with. So if you want to implement a dynamic language, a few things are just as if you implement any other language. Your language is going to have a syntax, so you need some sort of lexer, some parser. You often need some sort of compiler component, whether it's to bytecode or to something else. You will need a good garbage collector, and you need some sort of way to lay out your objects in memory. And those are often rather similar to other languages, so I'm not going to discuss all of them in detail. Your language implementation will need a way to deal with the control flow of your language, and this is trivially and slowly done in an interpreter that whether it's based on AST or bytecode. And if you go this path using AST or bytecode, you have a technically very well understood problem. Sometimes sometimes the control flow of your language is going to be a bit different than the sort of standard languages if you look at generators in Python, or some language have really complex demands, but that's quite rare. An example for this would be Prolog, where you have backtracking and non-determinism, but such examples are rare. So the very specific problem that you need to address when you want to make your dynamic language efficient is the problem of late binding. Because in most dynamic languages, all your lookups can only be done at runtime. So just looking at the source code, you cannot bind any of your names. And historically, dynamic languages have moved to ever later binding times. So for example, if you compare Smalltalk with, say, Python, in Smalltalk, a few things are bound at compile time, like the shape of your object is fixed. And in Python, the shape of the object can be completely arbitrary. So, and the mechanism that exists in the various languages are greatly different. So even though on the surface the languages might look similar, the real details vary greatly between all the various dynamic languages. And the mechanisms are also often very ad hoc, because the first implementation of dynamic languages were mostly interpreters. So people say, oh, let's do this, and it's easy. But then, of course, if you have to think about how to compile this, then you have big problems. Let's look at some examples. In Python, all the following things are late bound. Global names, modules can be loaded dynamically at runtime. Instance variables can be completely changed per instance. Methods are late bound. You can even change the methods of a class. You can change what class an object has. You can change the class hierarchy of your, you can say this class now has this other base class, and so on. A special case of late binding is dispatching, and dispatching is the question: how do I implement the operations that I want to do on my objects? And dispatching is, again, as late binding, there is quite complex, and the differences between the languages are very big. Usually, all the operations, that look like one operation on the language level, are internally split up into a large number of lookups, calls, dispatches, and usually that means that one single operation internally has a huge space of paths. And most of the paths are then actually uncommon, but you still need to deal with them somehow. And just to give you an example of the complexity involved, let's look at attribute reads in Python. So the details of this are not so important. What I want to more get at is how complex things can really become. So if you read an attribute m of an instance x in Python, which is also the mechanism used for method calls, the interpreter has to do, or the implementation has to do the following steps. First, you have to check for the special method __ get attribute on the object. If this special method is there, you just call it and be done. If it's not there, you have the lookup proceeds as follows. First, you look in the object directly, whether the object has an attribute of this name. If it's there, return it. And then if it's not there on the object, you're going to look in the classes of the object. And for that, you look at the method resolution order of the object and then just look in each class's dictionary for the attribute. If it's there, return it. If not, go on. Right, and if the attribute is found in a class, you're going to call a special method on the attribute value. And if the attribute is not found, there is yet another method to override this behavior. And then in the end, finally, if it's still not found, you're going to raise an attribute error. So something that looks rather simple on the surface, well, just read a field out of an object, internally is really a large space of different paths. And the same is true if you look at integer addition. I mean, this image is greatly simplified, but basically, if you want to add two objects, a large amount of things can happen. So basically, you can add numerical objects like integers, floats, longs, or complex numbers. But you can also add strings or concatenate lists or tuples, or you can also, the user-defined class can completely override what addition should do on these objects. And just a small part of the space, like if you add two objects A and B, and A is an integer and B is an integer, you're going to get an integer and perform integer addition. And then, of course, there are combinations. Like if you add a long to an integer, you will get a long, and and so on. So this, if you really draw out the graph, and in the beginning I tried, you need a large monitor. Right. So as we saw, one dispatch operation alone is rather complex, and the problem is, of course, that if you do many dispatch operations in a sequence, like you have two additions, then you get a combinatorial explosion of paths. So if you add A plus B and then add C, then the dispatch decision that the first operation takes will influence the dispatching of the second iteration because of the second operation. Because, for example, if A and B are integers, then the paths that the second addition takes is constrained by this knowledge. And so somehow, if you want to be a very efficient implementation, you need to deal with this concatenation of or explosion of paths. A further source of inefficiency is the boxing of primitive values, because you don't know the type of any of your objects. So many implementations actually have to box all objects, including primitives like integers and floats. And yes, I'm not going to talk about tagging here or other tricks. And the fact that your objects are going to be boxed puts a lot of pressure on your garbage collector, because if you just do a bit of arithmetic, you're going to create millions and millions of short-lived arithmetic boxes. And so you need a good garbage collector, which is clear anyway. But you would also like, by your compiler or by your implementation, to optimize away some of this overhead. Because if you have arithmetic, the lifetime of your boxes is known. So if you have, again, a plus b plus c, the intermediate result, a plus b, has a limited lifetime, because after the second addition, it's no longer going to be used. Right? So if you have a plus b plus c, and a and b are ints, and c is also an int, then the box that is made for a plus b will die pretty quickly. And so what you would like is that the result of a plus b is not allocated. The problem with this is that if you just look at a plus b, there are also paths where the result escapes, and something arbitrarily happens to it. Because C could be a user-defined class that overrides addition. So it could override addition to store the left operand into a file or into a globally accessible place or whatever. So you're always going to have a path where you cannot get rid of this allocation of a plus b. Okay, and now I get to the last problem, which is a bit of a side problem, but it's good to keep it in mind anyway. Many dynamic languages have reified frame access. What that means is that you can access the frame of functions that are currently running or that have been run at some point in the past and use reflection on them. You can say, give me the value of the local variable a in this function. And so languages that do that are Python, Smalltalk, and Ruby, and quite a few others. And the reason why you want this is, well, on the one hand, you can do all sorts of interesting hacks. On the other hand, one of the nice properties of such implementations is that you can write your debugger for the language in the language itself, which for things like Smalltalk that really have this sort of closed world approach is highly desirable. Implementing frames, these reified frames in an interpreter is trivial, because in an interpreter you need these frames anyway the interpreter is going to need the frames anyway to store its information. But the question is, how should reified frames work efficiently if a compiler is used? And I think not a lot of implementations actually solve this problem. Okay, so to summarize a bit the difficulties that I just identified, you need a way to implement the control flow of your language. You need to implement the various mechanisms for late binding and dispatching. Ideally, you want ways to optimize sequences of dispatches and also getting rid of the intermediate boxing in the process. And then you should keep reified frames in the back of your mind. Okay, so let's pause here for a moment. And are there any questions about the first few minutes? Or comments or additions or... Okay, and if everybody is happy with this list, I mean, does somebody want to add something? I will continue a bit. So the next part, I want to compare various approaches that are taken for implementing dynamic languages and look at how well they fit these requirements. And of course, if you implement a language, quite often you're going to implement some sort of virtual machine, and the language to write virtual machines in is C++. So a lot of these approaches are using C++ as an implementation language. And, well, the virtual machine can be purely interpretation-based. It can have some sort of static compiler. It can have a just-in-time compiler. And the sort of opposite approach is to reuse an existing virtual machine that has already been implemented and is highly tuned. And the candidates for that are, of course, the JVM or the CLR. So let's look at some examples. If you write your own virtual machine in C++, there's, for example, the CPython and Ruby, which are the standard Python and Ruby implementations, which are just C-based interpreters. There is V8, which is Google's JavaScript implementation, which is a method-based JIT. And then there's TraceMonkey, which is a tracing just-in-time compiler. And there are lots and lots of others, of course. On the other hand, you can build on top of an existing virtual machine. And for that, the examples would be Jython and IronPython, which are Python implementations for Java and the CLR, and their equivalents JRuby and IronRuby. And then there's a large ecosystem of various implementations that try to target the JVM or .NET, like Prologs, Lisps, Smalltalks, all sorts of things. So let's first look what happens if you implement your VM in C. And the first problem that you're going to hit is that if you program in C, it's quite hard to get all of the sort of meta goals that are listed in the beginning: flexibility, maintainability, simplicity, and performance. And in the Python case, this is rather obvious. So on the one hand, there is CPython, which is a very simple, flexible, bytecode-based virtual machine. It's evolvable. It has been maintained for many years, but it's really slow. Psycho, on the other hand, which is an extension to CPython, is a just-in-time compiler. It's extremely complex. It's hard to change, but it has excellent performance. And on the feature side of the spectrum, there's Stackless, which is a fork of CPython. And it adds a very nice feature. It adds very lightweight microthreads. But it was never incorporated back into CPython for complexity reasons. So the CPython developer said, yes, this is very nice, but it's going to make our VM much more complex, so we don't want it. Right, so if you use C++ or C++ to write an interpreter, you end up with the implementation itself is going to be mostly very easy. It's a quite well understood problem, how to write interpreters. It's portable between different architectures if you don't do any crazy tricks, and it's going to be slow. And so basically, if we go back to our requirements, implementing in C is not really going to, an interpreter in C is not going to help you with many of them. Yes, you can get the semantics right, and it's quite nicely from the source perspective, but nearly nothing is going to be fast. The only thing that's sort of easy is that, well, you can get reified frames. You have them, but again, they're slow. So the first reflex of many people that hear that, well, our interpreter is slow, is that the first reflex, oh, it's all the bytecode dispatch overhead. So we want to get rid of that, and thus they write a static compiler that is reusing the object model of the interpreter. And that gets nicely rid of the interpretation overhead, but it turns out that the interpretation overhead, like the bytecode dispatch overhead, is not really all that bad. So you get a 2 times speed up, which sounds very nice, but not if you look at the fact that dynamic languages are usually 60 or more times faster than C or something. And basically, in a static compiler, it's very, very hard to actually do anything about dispatch, late binding, or boxing, because the information you get just by looking at the source code is rather minimal. And any sort of static analysis is extremely hard and mostly doesn't work in realistic programs. And in the Python case, well, there are lots of people have had this thought. It's all the bytecode's fault. So there are lots and lots of projects that try it, and the most interesting one that's still going on is Cython, which is basically a compiler from a large subset of Python to C. And there are lots of discontinued experiments that have failed. So in a static compiler, you're not going to win much. I mean, your control flow is going to be faster, but all the other problems are not solved. And most of the static compilers, in that way that I know, just give up on reified frames. Okay, so to fundamentally attack some of the problems, you will have to use some sort of dynamic compiler. And if you need a dynamic or a just-in-time compiler, then you open a whole new can of worms. Your VM is going to be significantly more complex. You will have to compile your functions to assembler. You have to do type profiling and you have then to do inlining based on that. You need general optimizations on the resulting functions, and you need complex backends per architecture that you want to support. And basically, all this is from an engineering perspective, is extremely hard to pull off for a volunteer team. So it's not something that you just write together with 3 people on a weekend. And so the typical examples for method-based just-in-time compilers are, historically the Smalltalk on the self JITs, and they were extremely good. They took a long time to write. And the more modern examples would be V8 and partially Jagermonkey. Jagermonkey is a bit of a strange case. And also Psycho is an example of that, well, sort of. The reason why compilers are so much more complex than interpreters is that compilers are inherently bad encoding of semantics. So basically, the compiler will have to encode all the complex corner cases that your language has, all the strange parts, all the rare things that might conceivably happen, and often needs a huge bag of tricks to support the common cases well. And the interaction between all these tricks can be very complex and hard to foresee. And thus, this encoding of the language semantics into the compiler is quite often obscure and hard to change. And if you look at Psycho, Psycho is an excellent example for this slide. Psycho was written by, well, it's a one-man project, or rather a one-genius project. It was written by a guy over the course of 2 years, and in the end, it was extremely fast. But then it turned out that it was so complex that, on the one hand, nobody else ever managed to understand it. So a few people tried to help develop it, but didn't really get anywhere. And on the other hand, CPython continues to be developed. I mean, CPython always grows new features, and Psycho couldn't really keep up with the rapid development of CPython. So many of CPython's newer features are not supported, and because even the author at one point just gave up. And it's also not ported to anything else than 32-bit Intel machines, and it never will, because it would just mean a complete re-engineering of the whole thing. So one specific problem of sort of method-based just-in-time compilers that I want to point out here is the problem of dispatching dependencies. So let's go back to my favorite example of A plus B plus C. If you think internally that you have some generic operation add that is adding two numbers, then internally what the JIT has to compile is something like this. First you do an add of A and B, store it into an intermediate result, and then you add X and C to R. And then if you just inline these operations here in a language that, for example, just supports integers and floats, you get something quite complex. I mean, first you have the case of A could be an integer, B could be an integer, then you perform an integer addition, otherwise you perform a float addition. So at this point, you already lost, if you just do inlining, you already lost the information what X is. So at this point, it could either be a float or an integer. And then if you just inline the second addition, you're not making use of the fact that you already know, in theory, what X is, based on which of the paths you took to get there. So to improve this, you would have to duplicate this code and move it into the specific paths. But this is a rather, in general, a rather complex optimization that you then need to implement somehow. So to look at how method-based JITs meet the requirements, we get a list a bit like this. Well, you get good control flow support. You can handle your late binding and your dispatching given enough work. Dependency are rather hard, but it should still be possible somehow. And boxing, given enough manual work, you can probably write an optimization that tries to get rid of some of the boxings. Again, reified frames are hard. So along come tracing JITs. And how many here know how tracing JITs work and have been exposed to enough of Nikolai's talks? OK. So, well, I'm still going to give an introduction, and then you can tell me at which point you disagree. So tracing JIT compilers are a relatively recent approach to writing just-in-time compilers. And they have been pioneered by Michael Franz and Andreas Gall originally for Java VMs. But then they turned out to be also very well suited for dynamic languages. And examples for tracing JITs are TraceMonkey and LuaJIT, as well as Spur and PyPy. And those only sort off. And why sort off? I mean, they're clearly tracing JITs, but they're still quite different from those. So tracing JIT compilers, they took this idea from the Dynamo project. Dynamo was a dynamic rewriting of assembler. The nice thing about tracing JIT compilers is that it's conceptually much simpler than the type profiling that a typical method-based JIT has to do. So the basic assumptions of a tracing JIT are, A, the program will spend most of its time executing a loop, well, that's kind of clear. And B, several iterations of a loop are somehow likely to behave similarly. So the code path through a loop, the 2 iterations of a loop takes are similar. And so what a tracing VM does is it's usually a mixed mode execution environment. That means in the simplest form, it will contain both an interpreter and the tracer. And when you start running your program, at first, everything is simply interpreted. And while you interpret your program, you do some lightweight profiling. And then after a while, you find out, oh, this loop over there, it seems to be executed very often. I want to do something about that. And at this point, you start generating code specifically only for this loop. And you do this by starting to produce a trace. So what's a trace? A trace is basically just a sequential, a linear list of operations. And it's produced by recording every operation that the interpreter executes. So basically, the tracer observes what the interpreter is running, writes it down, and then in the end, at some point, it will turn this list of operations into machine code. And tracing stops usually after you reach a position in the program that you've already seen before. So if you trace a loop, you start at the beginning, write down your operations. At some point, you will reach a position in the program that you've seen before, and then tracing stops, and the trace thus ends with a jump to the beginning, to its own beginning. Right? So what happens if there is control flow in the loop? So for example, if there are if statements within the loop, you cannot just ignore the fact that you just took a decision and just recorded one path. So what you do is in the trace, you encode all these decisions, and you encode them in guards. And basically, guards are points where the control flow could have diverged to another path. And then, well, the next steps are code generation and then execution. And given that the list of operations is linear, it's very easy to turn into machine code because you just need to support linear paths. Your register allocator can be simple, and so on. And then you can also just immediately start executing the new loop you compiled, and you will do that until a guard fails. And after a guard failure, guard failure means that the assumptions that you did to produce the loop are no longer true. So afterwards, you will simply go back to interpret the program at the same point. So of course, in practice, there will be some control flow. So if a guard fails very often, things are inefficient because you go back to the interpreter all the time. So after a while, if a guard fails often enough, you just attach a new trace to this guard that starts from there. So how does a tracing JIT deal with dispatching? The trace contains the bytecode. Typically the trace contains the bytecode operations that the interpreter performed. And the bytecodes have, as we saw, complex internal semantics. For example, you would just see an add, and the add internally does rather complex things. So what the optimizer typically does is specialize this trace to the specific types that have been seen during tracing. So for example, if you trace a loop and the specific instance of this loop execution is working with integers, you will type specialize this trace to just contain the paths where you deal with integers. And to do that, the optimizer needs to duplicate some of the language semantics. It needs to know that add has these paths with integers and these paths with floats. And the nice thing about tracers is that it deals with dependencies between subsequent dispatches very well, because the paths through your loop are split very aggressively. Basically, control flow merging is happening only in the simplest approach, only at the beginning of the loop. And that means after a type check, you can assume, the rest of the trace can assume that the type of that variable. And that is not really true if you do inlining. Because if you do inlining, your paths will merge after the inline method, and you lose the information that you gained about the types again. And the reason why the tracer can be that aggressive about things is that it has to deal only with those paths that it has actually in practice observed. And in practice, the number of paths that is actually being run in the program is small, even though the potential space of paths is rather large. Similarly, you can deal with boxing in a tracing JIT. You can try to do escape analysis of operations only within the trace. So if you see an allocation, the thing is used for a bit, and it's stopped being used, you can try to remove the allocation. And you can do this because the trace is not containing the possibility that something very strange is happening. So you don't even see the paths where the object does escape. So some more technical advantages of a tracing JIT are that they can be added to an existing interpreter unobtrusively. That was indeed what happened with TraceMonkey and Lua JIT. And also the interpreter does a lot of the work of the tracer. You get automatic inlining for free, because if you trace a function call, you will just trace the inner operations and inline the function in that way. And it deals very well with finding the few common paths through the large path space. The bad points are, you're switching. On the one hand, you start with an interpreter, which is slow, and then the switching between interpretation and machine code execution is also slow. You might have problems with really complex control flows, because the sort of loop tangles, trace tangles that you get if you have really complex control flow are not really that optimal. And then another problem is you have granularity issues. Often the interpreter bytecode is a bit too coarse, because the interpreter bytecode does not show you any of the internal dispatching that's going on within the bytecode. So in theory, you would like a bit more detailed traces. Right, and so in this case, the optimizer needs to carefully re-add the decision tree that has been going on in the interpreter. So if we look at tracing JITs and how they meet the requirements, control flow works rather well, apart from really complex cases. Late binding can be handled quite well. Dispatching can be handled. Dependencies is greatly improved because you aggressively split your paths. And unboxing optimizations are much simpler because you can focus on trace stuff. And there's also a nice trick about reified frames. As soon as you try to reflectively introspect your frames, you simply leave the machine code execution and go back to the interpreter. And I think indeed this is something that TraceMonkey is doing. Sorry. And that means that the reflective access is not going to be fast, but in practice that doesn't really matter. Okay, so the last common approach is implementing your language on top of an object-oriented virtual machine. And if you do that, usually the approach that you take is you implement on top of the JVM or the CLR, usually by compiling to the bytecode of that VM. And you also have to implement the object model in either Java or C#. And this brings its own benefits of sets of benefits and problems. And I'm going to look specifically at JIT and IronPython in the following. The benefits of implementing on top of one of these VMs is clear. The first very nice thing is that you work at a much higher level of implementation as C. I mean, you don't need to deal with lots of low-level details that you need in C. Like the VM supplies you with a very good garbage collector. It supplies you with a JIT. And also you have much better interoperability than what the C level provides. So in the Python case, both JIT and IronPython integrate very well with their host VM. That means you can use Java libraries from JIT and .NET libraries from IronPython very nicely. Also, side point, they have much better threading than all other Python implementations. Of course, you also get a set of problems. And the biggest problem is that it's quite often very hard to map the specific context you have, concepts you have in your language to what the host virtual machine provides you with. And due to this semantic mismatch, your performance is often not improved at all, because the object model that you implement is very untypical for the code that you usually write in Java or .NET, C#. In particular, your object model typically has many megamorphic call sites. That means call sites that have tons and tons of receivers. And the JIT of your underlying VM is not going to like that very much. Also, I mean, the JVM has very good escape analysis. I don't know about the CLR. but it's not really helping you with boxing at all because there are always paths where your object is escaping. And to improve things, you can do very careful manual tuning, but since the VM also doesn't give you a lot of customization hooks or feedback, this manual tuning is extremely tedious. And right, in JIT and IronPython, it's quite clear that they are not faster than CPython, even though people hope that they would be. And IronPython is also cheating in that it really doesn't implement the feature of reified frames. And in the Python case, this is even still sort of easy. But if you look at an extreme example where the semantic mismatch between the language that you want to implement and the host VM is much larger, like Prolog, it's much, much harder to really get performance out of that. And most Prolog interpreters in Java are, or Prolog implementations in Java are impressively slow. Okay, so this slide is mostly about the JVM because I don't really know enough about the CLR to say something there. The problems that I described, the JVM is trying to address some of them in the future, and the JVM in particular is trying to add support for more languages by implementing tail calls, invoke dynamic, but it's not really there yet in the current virtual machines. And again, I'm going to predict that good performance, you're not going to get good performance for free. You still have to do a lot of manual tuning and careful controlling of what the VM is doing with your object model. And those VMs are not really meant for people who care about the exact shape of your assembler, which is what you do if you want to implement a language. And JRuby felt that very much. I mean, JRuby has tried to be a really fast Ruby implementation, which in theory should be easy because the standard Ruby implementation is really bad. And people poured a lot of effort into it. And it seems to work, so some cases are fast. But basically, things are also completely hotspot specific and also dependent on specific minor versions of hotspot. So if hotspot decides to slightly change its inlining threshold somewhere, then JRuby is going to be slow because some fast path is not properly inlined or something there is not. So what they did was really staring at assembler for months and deciding, maybe I can split my method here a bit like this, and then the JVM will inline it for me. And so this is not really something that is easy to do or fun. Right. So if you're on such a VM, you get good implementation of control flow. Late binding and dispatching can be handled if you put effort into it. Dependencies depends on how well the optimizations like the code that you have. Boxing is not necessarily improved because escape analysis doesn't help you. And reified frames are either you don't do them or they're going to be inefficient. Okay, so let's pause here again. Are there comments or questions? Cool. Okay, so now I get to what I've been up to in the last 6 years. So the PyPy project has been started in 2003 on a Python mailing list out of frustration with the existing Python implementations. And in the intermediate years, it has received a lot of funding, both from the European Union, from Google, Nokia, and a few smaller companies. The goal of the Python project, like this from the webpage, it aims at producing a flexible and fast Python implementation. But even though the name and sort of the goal statements only target Python, in practice, the whole technology stack is also reusable for other dynamic languages. And if you look at the status of languages we have implemented with PyPy, indeed, the most complete and good implementation of a language that we have is for Python, and indeed, the PyPy Python implementation is the fastest Python implementation in existence. It also contains a reasonably fast Prolog. It contains a sort of full Squeak implementation, but we have not tried the JIT technology with that yet. And it contains lots and lots of smaller experiments. So at some point, somebody tried to implement JavaScript with it. There's a small scheme interpreter. There's a very rudimentary Haskell interpreter. And all sorts of small made-up languages. So what is the approach that you take if you use PyPy to implement a language? Well, the goal is, of course, to achieve our original goals within one implementation. And you do that by not writing your virtual machine by hand at all, but instead you want to automatically generate it from a high-level description of the language that you're trying to implement. And this generation uses some metaprogramming techniques and aspects. And how do you describe a language if you want to implement it? Well, the way PyPy chose is that you write an interpreter for the language in a nice high-level language. And this interpreter is then translated or compiled to be a virtual machine that's running in various target environments. And most specifically, you can translate your interpreter to run as a VM in C. And we also have backends for .NET and the JVM, but I'm not going to talk about them. So PyPy particularly consists of two large parts. On the one hand, there's a Python interpreter written in RPython. And on the other hand, there is a compiler that turns RPython programs into C code. So what is RPython? RPython is a rather large subset of Python. And the subset is chosen in such a way that you can perform type inference on RPython code. But RPython is still a quite nice high-level language. I mean, it's really rather close to Python, except that you need to think about what the types of your variables are in specific places. And I want to differentiate it particularly against other meta-circular implementations like Squeak and Scheme 48, because Squeak is also a Smalltalk in Smalltalk. But the restricted subset of Smalltalk that they chose is really, really close to C. I mean, basically, it's just a very thin syntax layer on top of C. And that's not the case for PyPy. So how do you generate a VM? Well, we wrote this custom translation toolchain that takes an interpreter in RPython, turns it into C. And the main observation of this toolchain is that a lot of the aspects of the final VM are really completely orthogonal to your language semantics. So, and the idea is that those aspects are inserted automatically for you during translation. And examples for this is you don't want your interpreter to be confused by the fact that you put your garbage collections into it everywhere. And this is definitely the case if you implement in C. Like if you look at CPython, CPython uses reference counting, so the whole language implementation is littered by all these increase reference, decrease reference macros, and they just completely confuse what the language is supposed to do. So the other aspect that is inserted in a non-trivial way during translation is a tracing JIT compiler that is automatically tuned for the language that you're currently dealing with. And I'm going to talk about that soon. So the good points of PyPy approach is simplicity, because you can separate the language semantics from all the low-level details that don't really have anything to do with the language that you're trying to implement. On the other hand, you have flexibility, because RPython is really a nice high-level language. So it supports extensive metaprogramming. And you can do very interesting things with metaprogramming on the level of the interpreter. And the performance, well, the performance if you don't include a just-in-time compiler is reasonable. It's not particularly fast. It's on the level of a sort of good C-based interpreter. But if you include a just-in-time compiler, then it can be very fast. And well, of course, you cannot read this, but this is comparing the performance of CPython in blue and PyPy with a JIT in orange. And it's all normed to CPython for a set of benchmarks. Which benchmarks? I mean, if you want to know details about this, I can tell you. But well, I mean, the main message of this slide is that it's much faster, right? So it can be up to, I think it's probably 20 times faster for a few benchmarks, but it's usually at least 40% faster than CPython. So how does PyPy's just-in-time compiler work? It works by a concept that we like to call meta-tracing. And the meta-tracing approach emerged by looking at the problems that a sort of classical tracing JIT like TraceMonkey has. And the biggest problem is that we cannot use it because usually a tracer is really specific to the one language that you wrote the tracer for. And that wouldn't work for us because we want the tracer to work with a large variety of languages. Another problem is that the bytecode that you're tracing has often the wrong granularity. So it's actually, because in the trace you just see an add, but you would really like to know which path through the add space of paths has been taken. So in particular, the internals of one operations are not visible in the trace. So the PyPy's idea is, well, we write our interpreters in RPython, and we don't trace the execution of the program that's running on top, but we trace the execution of the interpreter of the RPython code. And for that, we wrote one generic RPython tracer, and this tracing process can be customized by a large set of hints that the interpreter author can insert into her interpreter to tweak this tracing process. And of course, the hope is then that if the meta tracer is well written, doesn't have bugs, that adding this JIT will not give you language-specific bugs. Of course, I mean, until you actually get all the bugs out of the meta tracer, a long time will have passed, but right. So there is a very immediate problem with meta tracing, and people that know about tracing JIT usually know this problem. If you trace something that is itself an interpreter, your main assumption of the tracing JITs is violated, because one of your main assumptions was that subsequent iterations of the same loop will have the same behavior. But if you trace an interpreter, that is not going to be the case, because two iterations of the interpreter will execute two different bytecodes usually. So we solved this problem with a very, very simple trick, and the details of that trick are not that important. But the idea is that you don't just trace one execution of the bytecode dispatch loop of the interpreter that you're tracing, but you continue tracing many iterations of that loop, and you do that as long as you reach exactly one iteration of the loop that is running in the user program on top. And then basically you get the effect that you trace, the length of your trace corresponds to the loop in the user program, but what you trace is really the interpreter executing this program. And basically if you do that, then you solve the problem of control flow in exactly the same way as a normal tracing JIT is also doing. And to optimize late binding and dispatching, you have a very, very simple idea. The object model is implementing this stuff anyway, and the object model is written in RPython, so you just trace through that. And so in that way, the meta tracer automatically records the fast path through these operations. And as in a normal tracing JIT, the meta tracer is very good at picking the common paths. Yes, I mean the common paths. And this doesn't always work without manual intervention from the start. So there are a number of hints that you fine-tune the process. For example, the interpreter author can say, never trace into this function, or always trace into this function. Or you can, if you encounter this function and it has constant arguments, you can constant fold it. And there are a number of hints like that. And if you use them, you can really get traces that are short and quite fast. To optimize boxing overhead, there is a very nice and powerful general optimization that operates on traces. And what this optimization tries to do is defer the allocations that you see within the trace for as long as possible. So if you see an allocation within the trace, and there's no immediate reason why this object needs to be allocated now, the allocation will be pushed down the trace as long as possible, and quite often it will, in that way, simply disappear. So allocations on the trace happen only in those rare paths where they are really needed. And the use cases for this, originally we wrote the technique mostly for arithmetic, so that you can get rid of the intermediate boxes if you perform many arithmetic operations. But then it turns out that it's really quite useful for lots of other things as well. For example, every time in Python, every time you do a function call, the argument passing is rather complex. So there's an intermediate object that just holds all the arguments and does the argument parsing. And this object doesn't live long, because you just, when you call it, you make it, and then you consume it immediately, and then it's gone. And then you will see in the trace the creation of that argument holder. You will do a few things on it, and then it's just gone, and that the optimization can remove that. Or even more powerfully, if you trace through, if you inline a function call in the trace, you will get a frame allocation, because the inner function needs a frame to run. And then that frame also just has a limited lifetime, so the optimization can remove it fully. In general, this is really just an engineering slide. There's nothing too deep about it. But in general, we have quite a nice way to deal with reified frames because we're writing interpreters, and the interpreters need some sort of object to hold to represent the frames anyway. So you can mark with a hint these frames as to the JIT to say that this is the frames that I'm dealing with. And the JIT will then special case them. And the attributes of these objects are stored as much as possible in the CPU registers or on the CPU stack. And on refactive access, you simply leave machine code and go back to interpretation. And this is really nothing too advanced. The only cool thing is that it's really implemented in a language-independent way, and you can use it for all the languages that you implement with PyPy. Right. Another sort of meta point is that our tracer tries to be as transparent as possible. So when you start writing an interpreter, you add some hints, and then you execute your code, and it's not fast. And then you need to understand why. So we try to have a lot of tools to understand how you should improve the placement of the hints to really get better code. And for that, the most important thing is that you actually look at the traces. You don't need to look at machine code, which is what you have to do if you try to do this tweaking on the JVM. The traces correspond rather closely to the RPython interpreter code. So the traces are just bits of your interpreter. And to actually look at the traces, we have nice visualization and profiling tools that tell you this part of the trace has been executed that often, and they connect to this other trace like this. And it's very, a lot of people have learned to read these traces that don't really work with the JIT usually, just to improve their interpreters. Okay, so I'm nearing the end of the talk, and I'm going to summarize a bit. So first, let me enumerate some drawbacks of our approach that I see. And the biggest drawback is, of course, now that we have all this machinery, it's very nice. But actually, to get there was a huge amount of effort, and it took many years. So if you start from scratch, it's not clear that you really want to do this sort of meta translation toolchain approach. Now that we have it, it's nice. The same thing is true about garbage collectors. Yes, it's nice that the garbage collector is completely separated from the language implementation, but writing this garbage collector that is inserted into the virtual machines was still quite a lot of hard work. And again, the same, the pattern repeats. The same is true about the dynamic compiler generation. We started trying to automatically get compilers from interpreters in, 2006. And this is version 5, and each version was a complete change of approach. And basically until we tried tracing, all the former approaches turned out to not work. And even the current approach is not perfect. I talked about the wrong granularity of traces in normal tracing JITs before, and our traces have a bit the opposite problem, which means that they're too detailed because they really spell out all the steps that the interpreter did to implement the behavior. Right, but on the positive side, I think that PyPy solves many of the problems that you have if you try to implement dynamic languages. The very nice thing from the point of view of the language implementer is that you can use a nice high-level language to implement your language, which is much easier than working in C. And also it has the benefit that you can analyze RPython code rather well. It's not that easy to actually analyze C code, for example. Which helps, for example, the JIT and other tools. PyPy gives you rather good feedback if you try to implement a language to learn and understand how you can place your hints better or otherwise improve things. And it gives you various mechanisms to express language semantics that are rather different. So that set of tools that we have in the hints, I think, is quite nice. Okay, so thanks very much, and I'm open for questions.
curious on the performance numbers with the tracing JIT. Did you guys find what the root cause? I mean, these are great results, right? Is it boxing?
You're talking about this and this, I guess.
Yeah, well, I mean, any of them are. 40% is still pretty good, right? I'm curious, though, what was it about CPython? Was it interpretation overhead? Was it function calling? Was it boxing?
I think it's a bit of all of them. I mean, basically, if you get 40%, then you really just get rid of the control flow overhead, because CPython really has some overhead in bytecode dispatching. And in those cases up here, you really get rid of all the method call overhead, all the finding the right method, boxing, and I don't really think that it's enough to implement just one of them well. And
But you don't have numbers on the individual?
no, it's probably hard to distribute the speedups to the various. I mean, maybe it would be instructive to just turn off some things and look what you still get, but I don't really think you can clearly separate these speedups. Yes?
So about these numbers, do they include the overhead or
Yes.
the tracing?
Yes. I mean, they're always with. There's no warm up going on. You just.
Can you quantify how much that overhead is out of the remaining time? Is it?
I mean, I can show you. Basically, I can show you a small demo. The problem with demos is that they're not very instructive because you just get 2 times the same behavior and one of them is fast. So if you use standard CPython, there is a benchmark included called PyStone, and you can say run this. So it takes 0.7 seconds, and then it just turns it into. Okay, if you do the same thing in PyPy. You get a much smaller number, and so that means that the compile time is bounded by this, right? Because it still also had to do the actual computation. So the overhead is in the. I mean, it's rather small. So.
And how about the memory consumption overhead? Is that significant, or can you generate more and more code?
It's okay. We're good at throwing away code that doesn't seem to be used anymore. But there is still a sizable overhead. So, for example, the largest program we tried, which is our own translation toolchain, we can speed that up with the JIT by about a factor of 2. But it will produce something like 300 megabytes of or 400 megabytes of assembler doing so. And it's a large program. I mean, I think it's 200,000 lines of Python code. So.
So when collecting these numbers, so you're only tracing loops?
Yes. No. The details of this are a bit complex. We are only tracing loops, and we are tracing. If you call a function that has a loop very often, we also trace from the beginning of the function to the loop.
Okay.
And right. So those are basically the 2 things we trace.
How about nested loops, recursion?
We don't deal with recursion. So basically, if you have recursion, you will just get a trace for the outer function, and in the middle you will have a call that just calls the same assembler again. But it's not like, I mean, the trace monkey people try to do that you just turn recursion also into a loop, but we never got there.
And nested loops?
Well, you do the usual thing. You first trace the inner loop, and then you attach the outer loop as a long side exit.
Okay. And can you quantify in the end, so if you look at the execution time, how much of that time is still spent in the interpreter, and how much is in the optimized code?
No, I don't know. I mean, I don't know numbers. It cannot be that much, because if you run this with, I can somehow turn the threshold very high, like this maybe. No. Maybe. I mean, if you run this purely in interpreted mode, it's slow. So the interpreter cannot run for a large percentage of time. But I don't know actual numbers. Yes?
So can you speak a bit about the experience in writing a new interpreter in this high-level language. So, let's say I want to come out and write a JavaScript interpreter in your new, or Python, whatever it's called. How do I, encode things like type semantics and things like that? I mean, how straightforward is that experience?
I mean, basically, it's a lot like implementing the same thing in Java or C#. I mean, basically, you write classes to represent your user-level objects. You write your operations on them as methods on the lower level or functions or whatever. The problem is, our Python is not the. I mean, there are drawbacks and disadvantages and advantages. The advantage is that the metaprogramming that you have in R Python is much better than in Java. So, for example, we have a rather high-level declaration-like syntax to define all the operations that you, for example, all the additions that you can do, and then this is turned with metaprogramming into much more code. So you can do this sort of generative approach, and that would be much harder to do in Java. The disadvantage is that there's type inference going on, and the error messages that you get sometimes from the type inferencer are completely inscrutable if you're unlucky. So this is one of the things that I don't like, but it's also really hard to improve on that. So. But yes, I mean, basically you can write nice things in a very short amount of time. So the Haskell interpreter, I mean, it doesn't have a parser. You have to write down the ASTs basically. But if you do that, it's mostly the core semantics of the language was implemented in 200 lines, and the performance is not horrible. I mean, of course, Haskell is completely static, and it's not clear whether our approach is helping that much there. But okay, other questions?
More questions?
So what is left to do? What are your next steps with this? I mean, is it now you go evangelize the world and get other people to use PyPy for Ruby and
that's
other
an
things?
excellent question. I mean, on the one hand, there's a lot of, really time-wise, there's lots of work that people do on the Python implementation. So simply being bug-to-bug compatible with CPython is lots of work. Because basically all the strange things that you can do in CPython has to be supported because somebody depends on them. So that's sort of the one side of things. The other side of things is basically, if you look at this slide, I mean, if you think about the fact that this end, the blue end, represents something like 60 times slower than C, and we speed up by, or even 100 times, we speed up by, say, 10 to 20 times in the best case. So the question is still, where does the other order of magnitude come from? And that is not clear to us at the moment. So we are considering doing a hybrid approach like Jagermonkey is doing, of thinking about ways to also generate, first generate a method-based JIT that just is a very fast compiler that doesn't optimize much, and then later doing tracing for the cases where it really matters. Or also, I mean, our tracer is not too slow, but it's also not really fast. So we are thinking about ways to optimize that. But basically, the completely immediate next steps are not entirely clear to us. So we don't have a clear plan what to do. I mean, we're quite happy with some of the numbers, but we don't have a completely clear plan what to do with the next order of magnitude. Okay, more questions? Yes?
Perhaps I just missed it, but I haven't heard you talk about the specific types of optimizations that you do on these traces after you collect them.
Right. So the most, it turns out that one of the most important optimizations that we really do is this object allocation removal. So if you see an allocation that you really put a lot of work into removing that. And then we do a large batch of other things. I mean, some of them Spur is also doing. For example, type strength, you call it guard strengthening, I think. We do that as well. We do read and write syncing. So if you read from the same field twice and you know that no code in between could have written to that, you just remove the second one. The same for writes. Well, constant folding, loop invariant code motion. I mean, our loop invariant code motion is not that effective, but it's quite okay. Yes?
In these optimizations, just a kind of a follow-up question. Do you make use of symbolic techniques, constraint solving techniques, or external tools?
No, the optimizations are just written by us, and some of them are a bit ad hoc. I mean, I think you can probably win. You can probably win a few 10% here and a few 10% there by being a bit more systematic in the optimizations. And also, our assembler backends are not particularly great. So another few percent you can probably win by doing better register allocation or something. Right.
Okay. Then let's thank our speaker again.
Thank you.